All right, so far in Chapter 11, we've learned a bunch of different tests for determining if a series converges or diverges. And in 11.7, we're going to look at strategy for testing series. So uh, we've learned a bunch of different things here, and I've got this written out in order. I say this is a good order to try the tests in, but really a lot of the time you can kind of jump to the correct thing. Um, if you notice right off that it's a geometric series, then use the geometric series stuff. If you notice right off it's a P series, then you can use this. And one other thing down here says if it involves a factorial, you almost always want to use the ratio test. But if it doesn't jump out at you immediately as to what to do, start up here at the top. Try the test for divergence on it. The test for divergence says if the terms don't go to zero as n goes to infinity, it's going to diverge. A lot of the time, well, I shouldn't say a lot of the time, but sometimes you can have something complicated, and this will take immediate care of it. But most of the time, the limit's going to be zero, meaning that the test for divergence doesn't tell you anything. So if that doesn't work, then if it's geometric or P-series or alternating, you want to try that. If it's not, then one of the comparison tests is probably the thing you're going to wind up using. The comparison test, what you usually want to compare to, is the series found by taking the dominant term in the numerator and denominator. A lot of the time that'll be a P-series or a geometric, and you can tell if it converges or diverges, and usually the other one's going to do the same thing, but the original series. But you still need to take some limits or establish an inequality to figure that out. All right, if a dominant term is sine, cosine, or tan, then instead of just using that as the thing to compare it to 1 or pi over 2, because sine and cosine are bounded by 1, and arctangent is bounded by pi over 2. If it involves a product of two or more types of functions or a factorial, ratio test is almost always what you want to use. And I've got the integral test down here at the end because that one doesn't really come up all that often. But if the formula for your terms, if it's something easy to integrate, then you can definitely use the integral test. So let's do some examples. I've got 14 examples, and I think I'm going to do a few of them here and split the rest of them up over at least 2 additional videos, probably maybe more. But let's look at these. Just glancing at these 3 guys here, number 2, I can tell immediately I want to use the ratio test because it's got that factorial. Number 1, I'd probably do the test for divergence on this thing, but when n goes to infinity, the top has an n and the bottom has an n squared for its dominant terms. So the terms of this thing are going to go to 0. So test for divergence fails, but we probably want to compare to, you'd want to compare it to n over n squared, which is the same as 1 over n. And this third one, let's look at it. The first thing I would think here is maybe rewrite it as n squared over e to the n cubed. And what can we do with that? We might be able to use the ratio test. And if the ratio test doesn't work, the integral test would work. Because you could integrate this function easily by letting doing a u substitution, let u equal n cubed. But let's go back up here and look at these. This first one where I said compare it to 1 over n, we know that this thing over here diverges because that's the harmonic series, P series with P equal 1. So if the comparison test works, well, Well, let me just say this. We want to compare these two things here. This diverges. If this is bigger than this, then automatically that other one's going to diverge too. But unfortunately, this -1 on top and the plus n on bottom, both of those things make this smaller than this thing. So our inequality goes the wrong way. So if we want to do this out formally, we have to use the limit comparison test. So let's compare these two. With the limit comparison test, you take the limit as n goes to infinity of one term over the other. And I could use n over n squared, but I'm not. I'm going to use 1 over n. So you put one of the terms up here, you put the other term. So you've got the series, the original series on top or bottom, and the other one is the thing you're comparing it to. So I'm going to rewrite this as 1 over n times n squared plus 1 over n minus 1. And when I would do that, I get n squared plus 1 over n squared minus n. Now what does that do when n goes to infinity? Well, this is my dominant term on top and bottom. So this gives me limit as n goes to infinity of n squared over n squared, which is 1. And then we have to remember, what does that mean for the limit comparison test? Well, if you get a finite number that's not 0, it means that both of those series do the same thing. Now, we know that this diverges here. And so this 1 tells us that this diverges as well. So our answer is that this series diverges. Okay, this next one, the factorial is the big giveaway on this one. Factorial says this is going to require the ratio test. Now my gut tells me that this is going to converge, but I don't know right off. So we'll use the ratio test. So this is a sub n. A sub n plus 1 is 10 to the n plus 1 over n plus 1 factorial. My cat. Come here, Graydon. He's meowing. Let's see. So take the limit as n goes to infinity of a sub n plus 1. So 10 to the n plus 1 over n plus 1 factorial. And my family is texting me. Let me turn that off. All right, so we've got 10 to the n plus 1 over n plus 1 factorial. That's the n plus 1 term. Then we'll divide by the nth term. So that'll be n factorial over 10 to the n. And I'm going to unroll some of this stuff. 10 to the n gets rewritten as 10 to the n times 10. Rather, this gets rewritten as 10 to the n times 10. N plus 1 factorial gets rewritten as n plus 1 times n factorial. That's times. And up top I've got n factorial. And then I've got 10 to the n down here. So this cancels with that. This cancels with that. And I'm left with n goes to infinity. On top I've got 10, and on bottom I've got n plus 1. That goes to 0. And then we have to think, what does that mean in terms of the ratio test? Getting a limit of 0, that's less than 1. Therefore, this series is absolutely convergent. And that's our answer. All right, I think I'll stop this video here and take care of my cats, and we'll pick up with example 3 in the next video.